Good morning to our project Skyline. This team is made up of Manuela Posada, Sofia Souza, Sergio Lat, and Arthur Arroyo.
In this project we have used Arduino Uno. This is a popular microcontroller board based on the ATmega 328P chip. It has digital and analog input-output pins that can be used to connect various sensors and modules, making it a versatile platform for projects like CanSat. Then, the BMP-180. This is a sensor module that measures barometric pressure and temperature. It can provide accurate altitude readings, which is useful for altitude tracking and environmental monitoring in a CanSat project.
APC-220. APC-220 is a radio communication model that operates in the 450 NEC frequency range. It can be used for wireless communication between the CanSat and the ground station, enabling wireless transmission and control. Quarter wave antenna. This type of antenna is commonly used for transmitting and receiving radio signals in CanSat projects. It's simple and compact, making it suitable for the limited space available in CanSat payloads.
The SD card module. This module allows the Arduino Uno to read and write data to an SD security digital card. It's useful for storing sensor data or other information collected during the CanSat's mission, providing a means of data logging and retrieving. Then the parachute. A parachute is essential for safely landing the CanSat after it has been deployed from the launch vehicle or balloon. It helps to slow down the descent and prevent damage to the payload upon landing. Lastly, the NV battery. This is a power source for the CanSat. It provides the necessary voltages to power the Arduino and other electronic components during the mission. Make sure to choose a battery with sufficient capacity to run the CanSat for the desired duration. Our mission is to detect and compare the altitude, temperature, and acceleration of the CanSat while being flown into the sky and into the atmosphere.
Some of our factors taken into account when making our CanSat were the weight, the parachute speed while descending, the size, and the area of the parachute.
The CanSat's primary mission is to determine the temperature and pressure of the atmosphere at different points during its descent, utilizing the BMP-180 sensor. Conducting atmospheric measurements is an essential part of space exploration, hence why it is the primary mission in our CanSat. Collecting the aforementioned data will give us more insight into the relationship between altitude, temperature, and pressure in the Earth's atmosphere.
So this is the CanSat. First, it is turned on by the switch. As you can see, it has its own power source, which is a 9-volt rechargeable battery. And here's the Arduino. It's a microcontroller. Basically, it stores the code and tells all the other components what to do. So it tells the BMP-180 to record the temperature and pressure and altitude of the CanSat. Also has the SD card, which is here to store all the information collected by the CanSat. And here it has an MPU 6050, which is part of the secondary mission. And it is used to calculate the acceleration of the CanSat. So as you can see here, this is the code of the CanSat for the primary mission. And in the serial monitor, it can be seen the data that's being collected by the CanSat. So the temperature, the altitude, and the pressure. Yeah.
Aside from the primary mission of determining temperature and pressure using the MPU 6050 sensor, we've also integrated a secondary mission to our CanSat project. We aim to assess environmental conditions such as air quality and radiation levels during this mission. By incorporating additional sensing into our payload, we'll collect valuable data to gain insights into our local conditions. This secondary mission not only enhances the scientific value of our project, but also provides us an excellent learning opportunity for our team.
Constraints. Ensure that our payload remains within the specific weight and size limits to facilitate successful launch and descent. Then, sensor accuracy and reliability. Selecting sensors with high accuracy and reliability to ensure precise data collection during the mission. The power consumption. Choosing components and sensors with low power requirements to optimize battery life and prolong mission duration. Trajectory. Calculate the descent trajectory and ensure the CanSat's stability during the descent to facilitate accuracy data collection. Considering these factors, we aim to design a robust and successful CanSat project that meets our mission's objectives and delivers valuable insight into atmospheric conditions.
To finish off, we've made sure that our CanSat is the most efficient, productive, and robust of them all. With all the precautions taken into account, we have ensured that the best